everyone, my name is Isabelle Alexandra, and I'm currently a high school senior from Indonesia. And for the next few minutes, I'm going to present my Talaria 2022 research project, which is a literature review of biomechatronic systems, namely exoskeletons, as well as other emerging technologies in the field. And for this project, I was mentored by Praful Purohit, who is a current PhD candidate in electrical engineering at Cornell University. So the reason I decided to research this topic is because I'm interested in engineering and robotics in general. And I was especially curious on how they are applied in the medical field. And I think this branch of engineering offers a lot of promising innovations that can revolutionize healthcare and medicine in the future. So firstly, what is biomechatronics? Well, biomechatronics is a subfield of mechatronics, which is an integration of various engineering fields like mechanical, electrical, informatics engineering as well. And biomechatronics is specifically applied in medicine and healthcare, among others. Usually it's for assistive purposes like rehabilitation and to regain the lost physical functions of the human limb. Some simple biomechatronic systems that you may recognize in day-to-day life are like pacemakers and implants, whereas the more advanced systems are a lot more complex in design, or like exoskeletons, deep brain stimulation, and surgical robots. And for this presentation, I will mainly be talking about exoskeletons. So an exoskeleton is a notable example of a wearable robot. It maps onto the anatomy of a human limb to restore its weak or lost functions. And depending on the part of the body that it assists, exoskeletons can be divided into upper limb, lower limb, and full body exoskeletons. So here are a few examples of upper limb exoskeletons. And on the left, we have the Hyundai Vest exoskeleton, or HVEX. And the HVEX is a passive exoskeleton. So it uses springs as its source of energy. So it's a mechanical source of energy instead of like an external power source. And the HVEX was designed to assist in overhead jobs that are mostly situated in industrial environments like automotive manufacturing centers. And then on the right side, we have hand exos, which is used for the rehabilitation of the hand. So it actuates or moves the 5 fingers while also preserving the palm and fingertip area, so the user can interact with everyday objects. Next, we have the lower limb exoskeletons. So on the left and in the video here is Bleek's Berkeley exoskeleton. It was developed by UC Berkeley, and it's an autonomous exoskeleton which was designed to assist in carrying heavy loads. And then on the right side, we also have RoboKnee, which is a knee brace that assists in walking. And the last example is full body exoskeletons. So these exoskeletons are typically used to augment and amplify human strength. So some examples here are HAL5, which stands for Hybrid Assistive Limb. And this was designed by Cyberdyne and the University of Tsukuba, Japan. And it was designed for rehabilitative and assistive functions, and is also applied in nursing care and for assisting the elderly. And in the middle here is the Kanagawa Power Assist Suit, which was designed to aid nurses in their daily work activities. And the right side is a wearable agri-robot, which, as its name entails, it was designed to assist agricultural workers in their day-to-day work. Next slide. And so in my paper, I also analyzed the components that are involved in making an exoskeleton system. So firstly, we have the main control unit, controllers, and they typically consist of microprocessors, which manage the command logo, as well as electrical components, which sends electrical signals to drive actuators and sensors, basically. And then we have the intelligence of the system, artificial intelligence, machine learning, and next up is sensors, which detects the information of the environment that the system interacts with. And most current exoskeleton designs can integrate as many as 40 different sensors, fun fact. And some of these examples include dynamic sensors, which are used to measure things like force, torque, and pressure. And some exoskeletons also use biosensors that detect signals like EEG or EMG, like myoelectricity sensors. And then lastly, we have actuators, which are responsible to provide the motion, forces, and torque to a system. And exoskeletons, the most commonly used actuators are these three: electric, pneumatic, and hydraulic actuators, though very recent developments have also included soft actuators, which can make the mechanical system of the exoskeleton more deformable, but also resilient at the same time. And based on the examples of exoskeletons that we looked at, as well as the components, we can identify what can and needs to be improved to leverage their utility and also increase the efficiency of these systems. For flexibility, developers of exoskeletons can consider using soft actuators and materials for the actuation and mechanical structures, so as to provide more degrees of movement for the user. And to make the systems more comfortable, they can also consider using lightweight and less rigid designs. It's kind of related to the flexibility point. And lastly, we can use non-invasive and wireless approaches in using and control of these exoskeletons. So I had an enjoyable experience working with my mentor. He's very knowledgeable in the field and helped me find study resources and pinpoint what exact topics that I was interested in researching for the program. And he guided me through the process of writing a paper, like from structuring the contents to how to cite sources properly. And outside of the research projects, we also discussed about STEM career paths and how to map the journey from going to undergrad studies to working in academia or entering the industry. And I found his advice really insightful because as a senior, I'm applying for college next semester, and having a mentor who's already an expert in the field of my interests to guide me was extremely beneficial. So what challenges did I face while working on this project? For me, the main issue that I faced was trying to configure meeting schedules with my mentor, since we have a 12-hour time zone difference. So it was very difficult. And I also had to start school in mid-July. So I had less time to work on the paper as before. And so time management became very critical, but thankfully we were able to meet and discuss more than once a week. And yeah, we completed the paper. From this experience, I gained lots of new knowledge on biomechatronics, robotics, and engineering. And I also developed technical skills in academic writing. But other than that, I also learned a lot of soft skills like communication, time management, as well as critical thinking. And as for my final remarks, I'm very grateful to Athena and Talaria for giving me the opportunity to attend this program. And I'd like to thank the Talaria staff for making this event possible. And most importantly, I'd like to give the biggest thanks to my mentor for guiding me throughout this research project. I couldn't have imagined completing it without him. I've learned a lot of new things and gained valuable experiences throughout this past 2 months. And I hope Talaria will continue to grow in the future and expand its reach to many students internationally. And that's all for my presentation. Thank you so much.